So summarizing what we've covered so far, basically we've done an analysis of the mean. First, we looked at how to estimate the mean of a population from from a sample, including the confidence interval on the population. Then we learned how to test whether a population that was sampled had the same mean as a known population. And third, we learned how to, by taking two samples, whether the populations that were sampled have equivalent means. This series of videos will learn how to do the same for the variance. So there will be 3 sections, each covering these points for the variance. And the first is section 2.2.2, in which we estimate the variance of a sampled population. So let's sort of go along the similar line of thinking that we followed before, in which we make repeat samples of our population. And our population has a variance of sigma squared. And if we do that, then it turns out that the measured variances within our sample will tend towards or they'll cluster about sigma squared. Okay, and the variance of our sample variances will approach 2 over n minus 1 times the variance of our population squared. So that's sigma to the 4th. Okay, so what will be the distribution of our sample variances? Well, I'll give you a hint. It's not going to be, it can't be Gaussian, because a Gaussian can extend to negative numbers. But it will tend to be positive. Well, the distribution of S squared will be positive. It will always be greater than 0. And it turns out that if the population has a normal distribution, S squared will follow a chi-squared distribution. Okay, so in this application, we're going to assume that the population has a normal distribution, and that's going to be sort of key here. Let's keep that in the back of our minds when we apply this. And a chi-squared distribution looks like this. So it's I'm just sketching this out. I'd like you to sketch this in your notes as well. So the axis is, again, the probability density, and the horizontal axis is S squared. So as we make repeated samples, S squared will be centered on, the mean will be near mu sigma squared, and it will vary about sigma squared. In terms of, so let's convert to a standard variable, and that involves normalization. Just as Z was a way of normalizing our measurements, or our sample means, our standard variable here, our normalizing variable here is chi-squared, and that's equal to the sample size minus 1 times the variance of our sample divided by sigma squared, the variance of our population. So if we convert that to our standard variable, we'll have a curve that looks, well, I'm just going to sketch it the same way. And you'll notice the dependence on n minus 1. So the width of this probability density function will depend on n. It'll tend to increase with the sample size. So this is just one curve for a given sample size that I've sketched here. Now, in order to define the confidence interval on our sigma squared from our measurement of variance of our sample, we have to define our critical bounds on chi-squared. And to do that, so let's see, so 1 minus alpha is going to be our confidence level. And so following the reasoning, analogous reasoning to what we did before, the right end of our probability density distribution will be alpha over 2. So this is going to be an unlikely range or value of chi-squared for our mean. And we would do the same on the left-hand side. But it's important to note that unlike the normal distribution, the chi-squared distribution is not symmetric. And of course, it can't be centered on 0. It starts at 0. So we have to define two values of chi-squared for the critical value. And the first is chi-squared sub alpha divided by 2 for n minus 1 degrees of freedom. And chi-squared alpha divided by 2 it's the value of chi-squared that bounding the area to the right of bounding the area to the right, and the area to the right is alpha over 2. It also happens to the area to the left of this value bounds is 1 minus alpha, but we're going to define sigma or chi-squared sub alpha over 2 based on the area it bounds to the right of that value. And on the left-hand side, this is chi-squared sub 1 minus alpha over 2 for given degrees of freedom, because chi-squared 1 minus alpha over 2 is the value of chi-squared bounding the area to the right, which in this case is 1 minus alpha over 2. Okay, so I hope you can see that this is how we're defining our alpha, right? So everything to the right of this, I guess, is 1 minus alpha over 2. And so we're going to use those critical values to define our confidence limits on confidence interval on sigma squared. And to do that, we'll know that the normalized value of our sample variance, which again is this chi-squared variable, is going to be less than chi-squared sub alpha over 2, our right-hand bound, and greater than chi-square sub 1 minus alpha over 2. And again, this is for n minus 1 degrees of freedom. Okay, and so solving for sigma squared, the bound is, it's going to be less than n minus 1 s squared divided by chi squared sub 1 minus alpha over 2, and it's going to be greater than n minus 1 times the variance over chi squared alpha over 2 n minus 1. Okay, and just for reference, the parallel equation for the mean was the mu, okay, was less than our estimate of the mu plus the absolute value of z sub alpha over 2 times s. This is a mu. And it was greater than x bar plus the absolute value of z sub alpha over 2. That was a minus. Sorry about that. X bar minus z sub alpha divided by 2 times s. Okay, so that's the parallel equation for the mean. This is what we use to estimate the confidence interval for the variance. And we measure we measure s squared from our sample. We know n minus 1, and we find this from a table. And there's one, you can look online for tables, but I'm providing you on our website. And so you can calculate these two bounds on the variance of our population. And again, 1 minus alpha is the confidence.